movie. Okay? So you consider your past experience with Spielberg movies, and this gives you a baseline probability of liking the new movie, right? If 1/3 of the time I like Spielberg movies, then that's sort of the base rate probability that you will like this one. Okay? So past experience tells you the base rate. And it may not be your own direct experience. It may be some other information you have that tells you the base rate. And then you adjust the base rate up or down using new information, signals, which you receive. So in this case, you might receive a signal from a critic, and you might receive a signal from a friend. Okay? And we're assuming that your tastes are in some way correlated with either the critic or your friends, whether positively or negatively, then you'll adjust. Right? So if the critic says it's a good movie, you know the critic is a bozo, then you'll adjust your probability downwards, etc. Okay? And raise your hand if you think I'm completely wrong about this, but I think that's pretty straightforwardly how we all think about inferring the probability of some unknown event about which we have limited information. Yeah? So these are the correct pieces of the puzzle according to probability theory, and I'm claiming that this is how most people infer probabilities. And I have one empirical check of that, which I just asked you and nobody demurred. So let's see what else we seem to get right. We seem to have a rough idea, not of just what the pieces are, but how those pieces of the puzzle are supposed to fit together, right? So I'm sorry, I realize this is insultingly simplistic. But if you've liked Steven Spielberg movies in the past, then holding the opinions of the critic and your friends constant, you're more likely to like the present movie, right? And then how do you take signals into consideration? Well, first you have to figure out the direction of the correlation, right? Do I usually agree with this person or not? And then you want to think about how strongly correlated. Well, this critic is all over the map. Sometimes I agree with them, sometimes I don't. And then you adjust your probability estimate towards if the critic or the friend, if your preferences are correlated, positively correlated, and away if they're negatively correlated. Okay? So this is all, as I say, sort of insultingly obvious. What we get wrong is how we actually put the pieces together. Okay? The actual sort of the details of it. We seem to understand by and large qualitatively how we're supposed to use base rates and signals, but we don't actually do it correctly quantitatively. And it's not just that we can't do the math, which most of us can't, but in fact that we behave as if we couldn't do the math. So it becomes somewhat of a moot point whether we can do the math or not. Possible reason, aka the reason. Knowing qualitatively how much information should change our estimates is easy, and knowing quantitatively exactly how much we should adjust our estimates is very difficult. Okay? And if it was just kind of random errors, sometimes high, sometimes low, it wouldn't be that big of a deal, but it turns out that in many cases it's predictably systematic and predictable and large errors in the inferences that we make. So this is what I mean by bounded rationality. There's just limits on what we can pull off. It goes far beyond just probability inference, but this is the first place we're going to really poke into it. Okay, so what we're going to do is, I'm going to segue now to the sort of quote-unquote standard model, which is not a product of economics at all. It's just straight probability theory, which we've hijacked and plugged into our models because we want to get simple, straightforward, consistent answers, and we don't really care how heroic our assumptions are. So we're going to go straight to the source, get some rigorous probability theory, and stick it into our model. And then I'm probably going to spend, I might just sort of show you very briefly a couple of anomalies, but I'm mostly going to spend the rest of this period getting really, really clear on what Bayes' rule is, how it's supposed to be applied, why it works the way it does. So if this is review for you, I apologize. Let's start with an example. The correct way to infer the probability of a hypothesis, H, given a signal I. Okay? So, for example, suppose that 1% of the population is HIV positive, and we have a test such that if we give the test to an HIV positive person, it will show up positive. The test will turn out positive with 99% probability, and if they're HIV negative, it will show up negative with 99% probability. Okay? We want to know what's the probability that somebody is HIV positive, given that we've seen a positive test. Okay? Sorry? Oh. Paul says it's half. That's just ludicrous, don't you think? That can't possibly be right. Of course, it's the right answer, or Paul wouldn't have said it, but because you have unbounded rationality, right? I think it's based on my limited experience. But let's get there. Let's see how it works. So the point of this is really not so much. This case is relatively straightforward to figure out. Mostly, I want you to see the framework of what the pieces of the process are. So H is our hypothesis, and the hypothesis is that the person's HIV positive. And then I is the signal. What's the result of their test? Okay, is it positive or negative? So here's a way to solve this problem, which you may very well have done if you've taken any probability classes, or maybe this is in 140, I don't know. But you can just build sort of like this is not a decision tree, it's just a probability tree, and just plug in these probabilities. So here's sort of whether or not you actually are HIV positive, which we don't yet know. And what we do know is that the probability that you're HIV positive is equal to 0.01, right? And the probability that you're HIV negative is equal to 0.99. That's the base rate, okay? You could say 0.01 is the base rate of HIV, 0.99 is the base rate of non-HIV, whatever. So these are base rates. And then we want to know what the probabilities, what are the conditional probabilities of seeing different signals given the true state of the world. Okay? So if the true state of the world is you're HIV positive, what is the probability of seeing, I'm using P and PR for probability interchangeably. What is the probability of seeing a signal test positive, given that the state of the world is that you're actually HIV positive? Okay? So that pipe, that vertical, sometimes called a mid, sometimes called a pipe, is, in this case, 0.99. We got that from up here. And I'm going to skip the second branch here and just go down to here and write in the probability of seeing the signal test positive, given a true state of the world, HIV negative, which is to say given that the hypothesis is false, is equal to 0.01, right? Because if you're HIV negative, you're going to get a negative result with probability 0.99, and a positive result with probability 0.01. And what we want to know is not the probability that you get a test positive if you're HIV positive, but what's the probability that you're HIV positive if you've gotten a test positive, okay? So what we want to do is we want to take the full set of cases in which you might get a positive test and see what percentage of those times is it because you're HIV positive, okay? So what's the probability that you're HIV positive conditional on, right, as a subset of the cases in which you get a positive result. And to get there, what we need is we need a couple of joint probabilities, okay? So these things are conditional probabilities. Well, that's what that vertical line means. It means probability of this thing conditional on that, this thing conditional on that. Now we need to sort of convert this information here into a couple of joint probabilities. What's the probability of being HIV positive and getting a positive test? What's the probability of being HIV negative and getting a positive test? And those two joint probabilities are going to tell us the total likelihood of getting a positive test, right? So the probability of being HIV positive and, that comma in the language of math is read and getting a signal of test positive. Okay, and by definition, the probability of HIV positive is independent of the probability to get a positive test conditional on being HIV. Right? By definition, that conditional probability is independent of that thing. So the probability of the two things happening at the same time is just the product of the two. Okay? So that's equal to the probability that you're HIV positive times the probability that you get a test that is positive. Oh, I hate how this slows down. Given that you're HIV positive. Yeah? And we know what that is. It's 0.01 times 0.99, which is equal to 0.0099. So pretty unlikely. And we can do the same thing down here. What's the probability that you're HIV negative, but that you nonetheless get a positive test? That is equal to the probability that you're HIV negative in the first place times the probability that you get a positive test, given that you're HIV negative, which is equal to 0.99 times 0.01. Oops, sorry. Okay, now it should be obvious that Paul's right, yes? It's just as likely that it's not as likely that you get a positive test result if you're HIV negative as it is that you get a positive test result if you're HIV positive. It's just that there's so many more people in the population who are HIV negative that the total proportion of cases in which a positive test result has come from an HIV negative individual is the same as the total proportion of cases in which a positive test result has come from a person who's HIV positive. Now, I'm going to stop writing on the screen because it's full. The math is this, and it's intuitively obvious from this by the time you get here, but just to finish it up, the probability that you are HIV positive, given that your test is positive, is equal to, right? What's the probability, what's the total proportion of the cases in which you get the result you're looking for, which is that you're HIV positive having gotten a positive test, out of the total probability set of getting a positive test result at all, which is the probability of that thing over the sum of the probabilities of two. Yes? Yes, it is. Thank you. Okay, so it's just equal to the probability that you are HIV positive and test positive divided by the probability that you tested positive in the first place. Okay? Which in this case is equal to 0.0099 divided by 0.099 times 2, which is 0.0198, which equals 0.5. Okay? This is Bayes' rule. Yes, did I make a mistake? Nope. So this is the probability. You're talking about this piece here? This one. So what that is if you're HIV positive, what's the probability that the test will show up positive? So that's a conditional probability going one way, from hypothesis to signal. Conditional on hypothesis, what's the probability of the signal? The thing we're always trying to do with Bayes' rule is to figure out what's the probability that the hypothesis is true given that we see the signal. That's that thing. Okay, so this reads as the probability that you're HIV positive conditional on getting a positive signal. Or what's the probability you're HIV positive if the test is positive? So that thing reads as conditional on or if or given that. And so what you do is you figure out, well, what's the likelihood that both of these things would have happened, that you were positive and got a positive test, and then just divide by all the different ways that you could have gotten a positive test. Okay? Yeah. So this comma is and. What's the probability that you're HIV positive? Are you talking about right there? No, that's here? This one? That should be a comma. Thank you. I'm very sorry. I apologize for my mistakes. Okay. If there's any others, speak now or forever hold your peace. Okay. My goal for the next 35 minutes, probably won't take the full 35, my goal is to make this radically not complicated. Okay? Like radically obvious. So let me take my best shot at it. Here's Bayes' rule. The probability of the hypothesis H given the signal I is the probability that the hypothesis is true and you get the signal divided by the probability that you would have gotten that signal without knowing whether the hypothesis is true or not, right? So the unconditional probability of seeing the signal. So what is that? Okay, so sorry, now we're getting into the heavily repetitive part. I got a mid-semester evaluation in my graduate class and somebody said, class is a little bit repetitive at times, and I thought to myself, that is because square one of basic pedagogy is to repeat the basic lesson over and over again. So the probability that the hypothesis is true conditional on the signal being seen is equal to the probability that the hypothesis is true and the signal is seen divided by the unconditional, so that's that thing, divided by the unconditional probability that the signal will be seen without knowing whether or not the hypothesis is true, that's that thing. Okay? So if you're plowing through the problem set or preparing for the exam and you just get wrapped around the axle and can't remember what the pieces of Bayes' rule are, come back to this slide. Where does this come from? It's very straightforward. It comes from the definition of a joint probability. Right? If two things are not independent of one another, right? Whether or not your test is positive is not independent of whether you have HIV. Right? Whether or not it rains today is independent of whether or not you are HIV positive. Whether or not you test positive is not independent of whether or not you're HIV positive. And to figure out a joint probability of two things occurring, when the probability of them occurring is when they're not probabilistically independent of one another, goes like this. Right? So let's say that there's some event A and some other event B. The probability of A being true, given that we know that B is true, is simply equal to the probability that, is this how I want to do it? Yes. No, it's not. Sorry, I'm making this mistake. The probability of A and B both being true at the same time is equal to the probability that A is true times the probability that B is true if you already know that A is true. And right, that makes perfect sense. So the probability that it's rainy and cold is equal to the probability that it's cold multiplied by the probability that it's rainy given that it's cold. Right? Rain and temperature are not independent of one another. It's more likely to be raining when it's cold around here. And so then we can just reverse this, right? And so we get the probability that, the conditional probability of B given A is equal to the joint probability that the two things happen at the same time divided by the probability that the second one happens in the first place. Okay, now, let me show you graphically what I mean by that. And I hope, this is the diagram that I hope makes Bayes' rule just so obvious that you will doubt me when I say that people are boundedly rational because it will be so obvious to you. Suppose I draw a box, a square box. May or may not actually be square. Let's try to make it square. And let's just say that its sides are of length 1, right? And so we have, yes? No, I intentionally did it the other way around to confuse you, because I want you to see how it generalizes. I think I'm right, aren't I? The probability of H given I is the probability of the two things happening. It's always the thing after the pipe that goes in the denominator. Yeah. So here's a box that's going to represent on this dimension the probability of event A happening. Sorry, no, that's not how I want to do this. It's not probability A. I'm going to do that in a second. This is just sort of this is just a box where the area of the box is 1. And I'm going to say that this space defines all possible outcomes in the world, right? So the weather could be rainy or not rainy, cold or not cold, blah, 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 or any number of other things. With probability 1, the weather will be something, right? So now let me draw two circles. This is going to be a Venn diagram. Here's a circle I'm going to call A, right? So if event A takes place, it means we're somewhere inside the circle, and the probability of event A taking place is the area of that circle, right? And A is going to be the event that it's cold, okay? And then let me draw another circle intersecting, and we'll call that B, and B is the event that it's rainy. And all the complement of A and B, all of this space around these two circles, is the event that it's neither rainy nor cold. Okay? So I think this is about right for Berkeley. This here, I don't want to fill one. That's A comma B. That's the event that it's rainy and cold. Okay? Now, it should be pretty obvious then, that first thing I wrote, that the probability that it's rainy and cold is equal to, well, what's the probability that it's cold? That's the area of this circle here, right? So times the probability that it's rainy given that it's cold. Okay? The probability that it's rainy given that it's cold. Does that make sense? First, you got to know what percentage of the time is it cold, and then taking that as our new universal set, what percentage of that time is it also rainy? Okay? That's all that is. And then you turn that on its head. That's the second thing I've gotten up here. And what you get is that the probability that it is rainy, that would be, right? Given that it's cold, if you get up one morning and somebody says to you, oh, it's cold out, but they don't tell you whether it's rainy or not, you want to know, should I take my umbrella? What's the probability that it's rainy and cold? Or sorry, what's the probability that it's rainy given that I already know it's cold? Is equal to, right? You just reverse this thing, and it's equal to the probability that it's both rainy and cold divided by the probability that it is where we at cold. That's B. Now, what's going on here, right? I'm just trying to drive this thing all the way down into the dirt. The probability that it's cold is the area of that circle, or egg. And the conditional probability that it's rainy, given that you already know it's cold, is the ratio between the part of that egg in which it's raining and the total area of the egg. Right? I mean, this is now sort of mind-numbingly obvious, I hope. Basically, what you're doing is you're just saying, well, take the event that it's rainy and cold. I don't want to know the unconditional probability of that being true on any given day. I want to re-normalize that probability by saying, what's the likelihood of that outcome, given that I already know it's cold? So the area of that football shape is the unconditional probability that it's rainy and cold, given that you know nothing about the weather. And then I'm just going to re-normalize it by saying, yeah, but what is that? What proportion of the probability that it's cold is that? That's Bayes' rule. That's all it is. Okay, and you can use this. You can use the tree diagram from the last slide to do Bayes' rule in a lot of cases, and you can use a box like this in similar or other cases. Okay, so I'm going to show you that next. Okay, new example. This one's going to show up in the next lecture. All right, choosing which mutual fund to invest in. One of the bigger mistakes most people make in their lives. I had a so-called retirement account several years ago that was invested in a fund that was supposed to, no, so it wasn't retirement account. This was savings, money that I had saved for when I graduated from graduate school, which was supposed to be in 2010. So naturally, I went to Fidelity and I said, put this in your 2010 account, right? Which should have, since it was a 2-year horizon, should have been a very secure, should have been almost entirely in bonds, right? And in fact, I graduated a year after the crash of 2008, a little bit more.